Then I'll start. Okay, hi everyone. Today I'm going to talk about quantum systems. Okay, first in quantum mechanics we have two types of particles, right? In quantum mechanics we say that the particles are indistinguishable. Which are the types of particles that we have? Okay, we have fermions and bosons. Do you know what are the characteristics of each type of particle?
I don't remember.
So bosons are integer spin. And fermions have half integer spin. Okay, and we want to understand the statistics that derive from that behavior. This means that fermions follow the Pauli exclusion principle, but bosons don't. Okay, now the idea is that we're going to try to do an exercise that will help us understand how these statistics play along. Okay, so the idea is that we have a system that has three energy levels. The ground state of the system has a degeneracy of 2, and we need to compute the partition function for each of the different distributions. Both Maxwell-Boltzmann, which is the classical statistical distribution, Fermi-Dirac, which is for fermions, and Bose-Einstein, which is for bosons. Okay, and we need to compute the partition function. Okay, let's start with fermions. Okay, So we have many different energies. So let's start with the first state. Let's write all the possible states. This is the ground state energy, 0, then epsilon 1 and epsilon 2. This is a three-level system. Okay? And I'm going to use different colors to represent each different state. So we know that the thing is that, okay, so what are the characteristics of fermions? They have Pauli exclusion, and they are indistinguishable, right? Okay, so let's start with energy, zero energy. And it's important that we are talking about spinless particles, okay? So the only degeneracy comes from the ground state. Okay? So for zero energy, both particles sit on the lowest state, and they occupy each of the states, each of the degeneracies. Let's see. Up and down. These are not spins, these are ground state degeneracy. Great. So then let's go to energy equal, and for simplicity, let's assume that epsilon 2 is 2 times epsilon 1. So I will just write epsilon. Okay, for a system with energy epsilon, we have two possibilities. Right? Then let's move on to energy equal to epsilon. Can you tell me the possible states of the two epsilon energy?
So like spin up and down.
So first we have a spin up here, and here let's say we have a particle. It's not spin. Remember that this up and down, it's just ground state degeneracy. Okay, then which state can we have?
Down.
So it would be the particle sitting here, and the other one in the two energy, right? And can we have any other state here, or these are all the possibilities that gives us two epsilon energy? Right? We can have a state that has two particles with energy epsilon, right? And then we can have another possibility, which is energy of 3 epsilon. So it could be one particle here and the other one here, right? That's the combination. And since there is there any state? Is there any other state here in this energy?
Or is it like up and down?
No, because the only state that has the two degeneracy is the ground state. So since we are not occupying the ground state, that's all we have to know. That's only the only thing that it's allowed. And remember that exchanging these particles do not change the system, because they are indistinguishable. So because of Pauli exclusion and indistinguishability, these are the only contributions to the possible states. So the only contributions to the partition function. So how would we write the grand canonical partition function? How many states we have at energy 0? Just one, right? Then let me just remind you the formula for the grand canonical partition function. Okay, then here we have energy epsilon. Sorry, we have to do it with the canonical ensemble, not grand canonical, so this is just beta epsilon. How many states do we have here? With epsilon energy? So we have two colors, so just two states. Then with 2 epsilon, here we have the number of states, and here we have the energy configuration, so it's 2 epsilon. So which number should I put here? It's just these 3 states, right? Because we have 3 colors. The last one is just one state, one possibility. So this is the partition function for fermions. Now for bosons, we don't have Pauli exclusion, but we have the particles are indistinguishable. So how many possibilities do we have here? So bosons can have exactly the same state. So first we start with the same distribution, right? Is there anything else that it's allowed?
I think we can put some epsilon up and down. I don't understand the question.
But in zero energy, can we put?
No.
Are there any other states allowed?
No.
Yes. In this case, there are, because we have bosons, so they can occupy the same state. So we can have both bosons on the up degeneracy, and we can have both bosons on the down degeneracy. Okay? Is it clear why? Because the ground state is degenerate, and we can have two bosons in the same state. but with fermions that's not possible.
Okay.
Okay, now let's go to energy equal 1. What epsilon? So we could have a particle here which is in the up and a particle in the epsilon state. Is there any other possibility? Can you tell me?
Yes.
Which one?
I don't know. I know that there is another possibility. I'm just not knowing what.
Sure. Okay, so the other possibility should be a particle in the down state and another particle here.
Okay.
Is there any other allowed possibility? No, because we cannot put any different configuration here because here we don't have any grounds, any degeneracy, so we cannot allow us to put anything else. Okay. Maybe if you have any questions, please let me know. Okay, so here, this is the energy of 2 epsilon. So which states are allowed? Maybe you can help me. Like this.
Spin down, spin up. Oh.
Spin down, and here.
No. And another one. Another
Great.
One.
Here,
Yes.
you say like
Yeah,
this.
And 1 in 3 epsilon. And 2 in epsilon.
Great. Perfect. Then we have energy of 3 epsilon. Just put it here.
One in epsilon, 1 in 2 epsilon.
Right. 1 in epsilon. 1 into epsilon. That's it. And for energy,
Both in 2 epsilon.
so what would be the partition function? So the first term is what?
3 times 1.
Right. So 3. Then
2 times e to power minus beta epsilon.
great. Then
3 e to power minus 2 epsilon beta.
right. Then
E to power minus 3 beta times epsilon.
great. And finally
E to power 4 epsilon beta.
Great. Okay. Now let's do Maxwell-Boltzmann. Which is classical particles. Okay, we have neither Pauli exclusion and these particles are distinguishable. Okay? So let's see how that changes things. For energy 0, what do we have?
Both body 0.
We have this one,
Oh, yeah.
but now they are distinguishable. So I need to put an index A and B for each part.
Yeah, there. So here is 4.
Great.
If we consider the spin.
Right. We have now the exchange of these. And what's the other possibilities? Both up, right? And bow down. Great. Then let me adjust right here. For energy equal epsilon, what possibilities do we have?
One epsilon spin up,
Right?
and the other 0 spin down.
This is
And both a body spin down and spin up, 2 states.
right. Okay. So here you told me this down, right? This like this. Do we have anything else?
We can change A and B.
Perfect. So now A sits here, and B sits here without. This is A. Great. Now with 2 epsilon, what are the possibilities?
One,
Here, right?
and A can spin down.
Then I can have both in the same state.
Yes.
And note, sorry, I didn't put the A and B here.
And for the first and second, they can exchange A and B.
Right. So you understand that
Right?
is this state is going to change if I have A and B exchanged?
It's not minimal.
Right. Great. So I have this. I can write like this, 2 times. Right. This is the number of permutations that I can do between particles, right? Since I only have 2 particles, I can only do one permutation. Okay. And let's do this for 3 energy. Just a second. Sorry. Okay, so we can have 1 here, right?
Yes.
A
A and B.
and
And
B.
we can exchange them.
Great. Which is the thing that we already know, right? And is there any other possibility? No, this is the only 2 possibilities, so 2 times this. And And for energy equal 4?
Both of them in 2 is 0. Just one state.
Right.
And
Both particles here, right?
can I ask about the exercise? Well, why is there just a specific spin in the energy epsilon or 2 epsilon?
Okay, so you're asking why is the ground the only thing that it's degenerate is the ground state, right?
Yes.
Okay, this is a constructed problem
Oh.
just to teach you how the statistics work.
Oh.
So it's in order that you can see what's going on and how to think about things. But usually in quantum mechanics, you could have a ground state with degeneracy, or any other level could have degeneracy. And the idea is that you have to think in terms of like, this is just to teach you how to think about those types of problems. Okay.
Another question is it possible for classical particle to have spin?
No. Okay. So quantum spin is a quantum mechanical property,
Yes.
but you can actually have a degree of freedom. You can actually think of problems that are interesting. That in some sense there are classical particles that have only 2 values. For example, if you're doing computer science, then you can have bits of 1 and 0. So you can have something classical that has only 2 possibilities.
Oh, yes.
So that's a good question. So let me write and actually statistical physics is very useful to computer science.
Yeah.
So what would be the partition function? Can you help me? Which would be the
4
first?
times 1 plus 4 times e to the power 4 minus beta epsilon plus 5 times e to the power minus 2 beta epsilon
Right.
plus 2 times e to the power minus
Minus
3 beta epsilon
Great.
plus e to the power 4 minus 4 beta epsilon.
Great. Great. Do you have any questions about what we just did? Anything?
Why is it like 4 plus 4 plus 5? Like,
Here?
yes.
Okay, so 4, it's this is the number of states that have that energy, right?
Oh, okay.
So we are understanding that in quantum mechanics, we don't actually the right way to think about things is with the energy, right? Because we diagonalize our Hamiltonian and we get specific energies. We don't know about position or momentum. We don't know which are the good quantum numbers, but we know that it's related to the energy of the system, right? So instead of looking to other properties like that, in statistical quantum mechanics, we actually want to look at the energies. And that tells us different things. And actually, you can see here in this problem that we are not talking about momentum, anything. We just are given some properties of a system, and then we can derive the statistics, which is pretty neat. Okay?
Like 0, okay, in the 0th state we have like, so the first 4 is like it correlates to the 0th state.
This one, right. It's the ground state, the 0 energy state.
Yeah, but like I don't understand, so like why 4? Like how
Okay. Okay, why in this case 4, or in general, why do we have different, why is the
like
ground
why
state?
in theory it's like 4 and then 5, like why in like the 2 epsilon case it's 5, like I don't understand.
Great. The idea is that we have two possibilities, right? Here, the ground state has degeneracy of 2, right?
Okay.
So the particles here can have two different states.
Okay.
Okay. So in this case, since we can distinguish between particles,
Okay.
it's not only about which particle. If a particle is sitting here, it's also important which of the particles are sitting here.
Okay.
Okay. So the idea is that we have a particle A and particle B. So we can have particle A up, particle A down, and and the one in B. But we can also exchange them,
Okay.
right? And we will have a different state because we can distinguish particles. But in the case of this state, if we exchange A and B, we doesn't have any problem. Like we have exactly the same state, right?
Okay.
Because the particles are sitting on the same energy.
Okay.
Good?
Okay. And in the rest it's not the case. בשאר כאילו המקרים זה לא המקרה, כאילו בגראונד סטייט זה כאילו 4 ובאפסילון 1 זה גם כן 4 כי כאילו
פה?
לא, למעלה. כן.
פה?
כי כאילו הרי המקדם של כל אנרגיה זה כמות כאילו המצבים האפשריים בכל אנרגיה.
Right. Exactly.
Okay.
Exactly, because we can exchange this, and these are not the same states. You can see that if the particle is the one that is sitting in this energy level, it matters which of the one, like we are actually performing some change in the energy.
Okay.
Okay, great.
Another question about
Sure.
the maximum Boltzmann distribution is that in the cloud we have the V is equal to V1 times V2. Is it possible here?
What? Sorry, I didn't understand.
Is it check that V is equal to V1 times V2?
You mean to do the factorization?
Oh yes.
Right. Okay. So actually, what we are doing here, it's just so the problem here is that we don't have exactly the same states. Let me think about it. So we need to be aware, because do you remember that we have like the partition function? You're kind of right. It's a good opportunity to explain something. So the partition function is the total partition function. You write it like this, right? The only thing is that here it's up to a degeneracy factor, right? So you can have something that is degenerate. So the idea is that we are taking care of how to count about degeneracy. If you see, it would be very hard, like you're constructing each of the states of the partition function. You wouldn't be separating for one, like you couldn't separate for one particle because you need to take into account the interaction between the particles. I don't know if that makes sense. But it's a good question, because the idea is that actually you have some sort of degeneracy, and degeneracy is very important in the statistics. Play a huge role in how you look at this type of problems. Because after all, this is a problem of counting, right? We're just counting how many states we have, and it's crucial to understanding all the possibilities and to understanding the statistical distribution. Okay, so let's go to Bose-Einstein distribution, something that you did today with Stas. Okay, so we can. It would be very useful what I'm going to show you now. Okay. So the idea here is that, do you remember how do we compute the grand canonical partition function? We sum over all the possible number of particles, right? E to the minus beta epsilon okay. So if you look at this formula, I just told you that this is the partition function, but that's not actually the case. Why? Because I am just taking for granted what is epsilon, right? So this is the partition function for the energy epsilon. So your question was right on spot in the sense that here, instead of using every I, we use energy levels. So if you want to write the partition function, you will have to take into account each of the energy levels, because these are the good. The energies are the things that are well defined in quantum mechanical problems, right? So, for example, if we have bosons, and this is the partition function for a specific epsilon, then can you tell me what is this equal to? So do you agree with me that I can just do this? And what is this?
It's a geometric sum.
Great. Now, how would I compute the, we're interested in asking ourselves how many particles are in each state, right? For a given energy. That's what we did here, actually, right? But we want to do it a little bit more general. So how do we compute number of particles? It's just the derivative with respect to the chemical potential, right? So this expected number of particles is just kBt d ln z epsilon d mu. And you can just perform this derivative, which is very, very easy, and you will get that it's actually epsilon minus it's not minus. So this would be the contribution. This would be then the number of states at each energy as a function of temperature. And this would be this is the grand canonical partition function for bosons in general. Any questions about how I get these things? Great. Okay. Now let's do fermions. By the way, what time is it? We have a fermions. Okay, just the same. Should I put here from 0 to infinity? Actually, no, I only have to put 0 and 1, right? Because I cannot have two fermions on the same energy state. Do you agree? So just as before, but this is not, of course, this is not a geometric sum, but it's actually easier, right? So the first term would be what? 1, and the second term would be that's it, right? And then if we try to compute the number of electrons on the energy level epsilon, what shall we do? KBT, right? We know this from, it's always the same message. And this is for energy epsilon. Whenever you have the partition function, you can do the bridge with thermodynamics, and then everything, any thermodynamical quantity is very easy to find, just making derivatives. Right? And this will just be ala beta epsilon minus mu plus 1. So let's try to understand what is going on here. This is a pretty neat formula. This is like a feature that you have a quantum mechanical problem. A classical problem wouldn't have this type of distribution. Why? Because we are enforcing here Pauli exclusion principle, right? You can, like, it's notably seen. Okay, so we're trying to do. Okay. So at t goes to 0, this term actually, what would happen to beta? As t goes to 0, beta goes to right. So this term would be, okay, so here we have two limits, right? If mu is bigger than, then we would have just one. And if epsilon is bigger than mu, what we will have?
0.
Right? So it's either 1 or 0. But the thing is that as you increase temperature, this is, okay, so this is a step function when t is 0, but t bigger than 0, what will you do? You will have some something very similar, but you will have some smoothness on the curve. Okay? So you can see that the electron that has more energy in this distribution, here this is called energy at Fermi energy. And this is the, as t goes to a finite number, then you have, this would be the energy of the electron with highest energy. Okay. Just to finish up, let's do a computation. So let's compute the energy of an ideal gas of electrons. Okay. So actually, this is very interesting. We can actually compute the internal energy from this basic principle that this is a statistical quantity and that we know the probabilities of each of the states. So we could have the internal energy, it would be just an integral up to up to Fermi energy at t goes to 0 of epsilon e to the minus beta to the density of states, the epsilon. And if we are talking about free particles, then this would just be epsilon times b 2 pi squared over 2m h bar and this would just be 2 pi squared Notice that if t is different than 0, then we will have to take a different. We would have to put a density of states that is different than a step function, and then we would have to take the limit to infinity instead of energy at Fermi. Now we want to compare that with from here. If do you agree with me that you can here compute the what Fermi's energy is from here? Because we just have to put that we have n particles, and then from there solve for energy at Fermi, right? And let's compare our results with the ideal gas. Okay. So let me just tell you the results for the Fermi level energy. It will be h bar squared over 2m. Instead of putting here energy, we just put their number of particles and we will have the same average. Then, for example, for pressure, we just know that it's the derivative of the internal energy with respect to V. And just the result, it would be minus 2 pi squared h1 cubed 2 over 5. This multiplied by minus 2 over 3. And this would be 2/3 of UV. So, from here we have that the free energy would be 1.half, and applying the ideal gas formula, we will have that this would be the internal energy of the system. Okay. Thank you very much. Do you have any questions?